Thank you everyone for coming to another search seminar. Brennan, you have 50 minutes. Take it away.
Thank you so much. Thank you all for continuing this great workshop series. I'm really glad to be able to present this work joint with my longtime co-author and colleague Naraya Kun, who's in Turkey, although currently at a visiting position in Iowa. So the topic here, and I don't know if I love the title here, but this the topic is I think one that I've been interested in a long time. Um, when we think about consumer search, there's kind of two things that I think are kind of important to include in our models. One is the fact that search actually does take effort, but it's not just costly effort. It's also that it requires time to gather the information. And especially over the course of searching, we sometimes get worn down, that we are kind of worn out from fatigue of some sort or another. And as a result, we're willing to pay more over time. So recent paper I had together with Dominic Coey and Brad Larson documented this with failed auction attempts, that when you lose an item in one auction on eBay, if we follow you to another auction of the same item later on, you tend to raise your bid each time, the highest bid that you would have given. And also, Limo and Peterson showed this with rental truck reservations in terms of people offering more as they get closer to the time that they needed the truck. The other observation that we're all pretty familiar with is there's lots of price dispersion in markets with search. This is kind of intertemporal, meaning like there's lots of prices being quoted at the same time, but also over time, these prices that people are willing to accept have a lot of variation in them as well. The story that we're focusing in on what might be responsible for this time-dependent search is that eventually unsuccessful search is going to be costly. If you're searching for something, ultimately you have a purpose in mind. And if you don't get it in time for that purpose, then you have to find some sort of inferior option to replace it. So for instance, if you get a new job offer, and you've got a bit of time before you have to move there, then you want to start looking for housing options. And during that time, of course, you don't have to move right away. But if the job starts and you still haven't found the new apartment or new house, then you're going to have to do something like hotel rooms for a while. It's not going to be as desirable. Likewise, when you have some sort of event coming up, like a birthday or anniversary, and you want to get a gift for your loved one, you've got the time between now and then to find it, but giving the gift after the event doesn't go over so well. So there's kind of this built-in deadline. And you could, of course, even think about this for like travel arrangements as well, that there is a deadline, and if you don't meet it, then you'll have to cancel or postpone your intended travel. So what we see then is that over the duration of your search, you can adjust your search strategies. And one of those adjustments you can make is in changing the reservation price, what you're willing to accept from this distribution of potential prices you get quoted. The other thing that you can do is you can work harder if you want to change the intensity with which you search, which in our model is going to be affecting how frequently you get quoted price offers, visit more stores, spend more time looking on the internet, those sort of decisions. Of course, we're also interested in doing this in an equilibrium search setting. We want to think, how are the sellers going to be anticipating these changing search strategies of the buyers? In our model, we're going to have the buyers are going to be somewhere in the process of the search, and there'll be this steady state distribution of how many are at each point in that search process. The sellers are going to know what that distribution looks like, but they're not going to be able to observe the individual who's shown up at their website and say, oh, I know you've been searching for a month for this item. And as a result, then they have to make a trade-off here of saying I can either charge a high price, which will only be accepted by people who are really close to their eventual deadline, or I can choose a lower price, and that way more people will accept it, because of course it'll still be acceptable to the people who are close to their deadline, but it'll also catch some of the people who have more time on the clock left. And as long as you have multiple prices that are equally profitable, the trade-off exactly balanced, then we can have price dispersion and equilibrium. So the main contributions we see from this paper are, the first is that we're incorporating both the search intensity and this deadline pressure in the same model. We've worked on previous papers that have some component of deadlines. In fact, the closest of this is one that was in the setting of labor search, as your unemployment benefits are going to get cut off at some point. Putting this into a consumer search setting is new for us, but also putting it into this component of search intensity is also something that we haven't done before. The two kind of really cool things that kind of methodologically we get out of this is, number one, we can fully characterize this model if we have just exogenous intensity where it stays constant throughout. We get some pretty rich pricing dynamics that I think are interesting, we'll go through today. And then we also have developed a computational algorithm to solve out this model under the endogenous intensity, which requires some careful finesse with some differential equations and a numerical solution. But I think that process is pretty interesting and hopefully useful to others as well. In terms of the results of the model, we do get this price dispersion under a generic set of parameters. Generally, there's going to be a continuous portion of that price distribution, and then there'll also be some atoms where the firms are offering for some prices with positive mass. The sellers are going to have some of the search span that they're just not willing to make offers that target that group. That is, there'll be some buyers that they say, well, I know you're out there. You may even be willing to pay more than some of these other people I'm targeting, but there's not enough of you to make it worthwhile. So they're kind of ignored in the pricing scheme. The other thing that we see from building in both the search intensity and deadlines is that there's a sort of strategic substitute component to this. That is, if they didn't have the option to increase their search intensity, then they choose their reservation price strategy for the whole sequence of their search duration. But once we introduce some option to ramp up their intensity over time, they do that. And so that both the reservation prices and the search effort are going up. But they kind of substitute for one another in that I don't have to raise my reservation prices quite as much if instead I can work harder to find more quotes close to my deadline. The kind of interaction of these, since we're doing this with endogenous pricing, gives us that there's kind of more competition among the firms, and therefore it lowers the prices in equilibrium when search intensity is available. Some related literature. Of course, there's lots of people that we could cite in all of these, but in the equilibrium search, I just wanted to mention both Diamond and Albrecht, because this kind of underscores the pricing decision here of trade-offs between how many people are going to be more desperate versus less desperate. In both of these papers, it's kind of discrete whether you're desperate or not. And in Diamond, it was just a fixed feature, like I'm either desperate or I'm not. Albrecht, you had some chance of changing over time. Neither of these have kind of this continuum of like slowly counting down the clock in a deterministic way. It's also related, like I said, my co-author and I have done a number of variations on thinking about deadlines, whether in the labor market, the marriage market, recently also thinking about this outside of steady state. That's the 2022 paper. Hoping that we're going to be able to fill in some important gaps here in understanding what this does in this consumer search setting. Bargaining on a deadline, there's a fair amount of work in thinking about when you have some sort of negotiation going on with imperfect information and the process of alternating offers as you get closer and closer to a deadline. This is relevant in terms of there's a similar feel of changing your strategy as you get closer to that deadline. But the difference here is that in those settings, the deadline is known of the person that you're negotiating with, and they're trying to figure out the information that's missing is how much is it worth to the person. We've kind of reversed that here, where everyone's going to know actually what it's worth to you if they knew your type, your time that you have left. But what's not known is the deadline of the person that's shown up to make the purchase. And finally, the couple papers we should mention here in terms of search intensity. There's actually a fair amount I'm not mentioning here in terms of search intensity on the labor market. But in terms of choosing search intensity in consumer search market, the kind of papers that come to mind here are especially those that are selecting how many quotes am I going to receive. And those are usually more in a simultaneous search setting, although Choi is in a sequential setting. So that has some relevance for this as well, although without the deadlines built into it. So that said, let's get to the model. Environment here, we're going to think about time passing continuously. This allows us to use the power of differential equations later on in solving this. But there's going to be a bunch of very small buyers and very small sellers on both sides of the market. The sellers are completely homogeneous. They all face the same costs. The buyers are going to be homogeneous except for when they enter the market, they're all going to look identical at the time they enter the market. But their experience as they go through the market could differ and therefore give us a little bit of endogenous heterogeneity. The sellers get to choose a price that they're going to post. And you can think of this as like the firm just commits to a single price the whole time, and then different firms charge different prices. Under that interpretation, you'd want to think that the buyers don't know which firms offer which prices. Or alternatively, you could think about it that the sellers, each time a person comes to them, draw a price to quote to them from this distribution that's going to come out in equilibrium. Buyers, on the other hand, are going to be choosing at each moment how hard should they search, the search effort S, and they're going to be choosing what prices they're willing to accept. So any price at or below R, they'll go ahead and execute the trade. But for the buyers, then importantly here, they don't have any disagreement of how much this item is worth. We're all going to say that if we're searching for me, it's Legos for my kids for their birthdays, then we all agree the Lego set's worth $100 but what I'm willing to pay for it at any given moment might be lower than $100 if I'm looking for a deal. On the buyer side, to get a little more details here, so we're going to have the buyers entering into the market at a steady rate. This is a kind of Poisson process, but since there's a large number of them, then it's going to be basically smoothed out so that we have delta more of them coming to the market every time. When they enter, we're going to give them cap T units of time as their grace period. And during the grace period, they've got this flow of utility B. You can think about this as like goodwill. You could set B equal to 0 and say, well, during that time, there's no impact. You could actually even make B negative so that there's a cost of search during this time. But the important thing is once we expire, once the clock ticks down from T to 0, there's a switch, and that cost of continued search now drops to D. So this would be, I'm in the doghouse because I forgot to get the present for my son. Also for the search effort, like I said, we're allowing them to choose S at each point in time. That's going to have a utility cost that we're putting as quadratic here. We can generalize that a little bit. And the reason why S matters is because that determines how frequently you bump into sellers. There's two components here on the matching rate, if you will. The first is mu, which is a exogenous fixed amount. You could think about this as just you bump into people naturally, or you see billboards on as you drive down the interstate. You happen to get emails from companies you've interacted with in the past. So those just happen on their own, even if you're not putting any effort at all. But then you can put in extra effort, and whatever S you choose, then lambda times S determines how much extra quotes you obtain because of that. So whenever you do get a quote, whether from either source, then that quote comes as a price draw out of this distribution F. You look at it and you have to accept it, or if you reject it, then it's without potential for future recall, so it's gone forever. If you do accept it, then you get your consumer surplus, that's the X minus P, and you leave the market, you're done. If you reject it, then you continue your search.
Just going back to what you had said earlier, the firms are going to keep the same price, or they're able to vary it here?
Well, what we're going to think about this is in steady state is that the distribution FP is going to be in steady over time. So you can think about this as each firm is one of those points in the distribution, they hold that forever, or you can think about every firm is just randomizing with this mixed strategy FP.
Thank you.
Okay, so Bellman equations here, just walking through briefly. So the flow value that we've got to think about people who are expired separately from the people who are still in their grace period. The flow value for an expired person, say what's the benefit of continued search? Well, I'm going to have this flow utility D, which again, D could be negative. So it's like, it's costly for me once I've hit my deadline, and I keep incurring that cost as long as I'm still in search. Then I also have this quadratic cost of my search effort. And then the remaining term, of course, is I'm going to be, whenever I do encounter offer at this lambda times S plus mu, then I get the draw from the distribution, and I accept any price at or below R0. In fact, there won't be any prices higher than R0 because there's not going to be anyone who's willing to accept them in equilibrium. So then my change here is I get the consumer surplus X minus P, but I also give up the search, which is why the minus V0 is in there. That's my change in utility from having accepted this price offer and abandoned further search. If we move to people who are before their deadline, then we look almost the same. You can see that, for instance, the integral looks almost the same, except for I potentially have chosen a different RZ instead of R0. I can be more picky because I still have some time. And so I'll reject some prices that I might accept once I've hit expiration. And of course, I've also allowed SZ to change. I can choose a different level of intensity at each instant of my search. My flow utility instead of D is B, which was higher. And then there's the V prime term. What that's capturing is that the clock is steadily ticking down. My state is changing at a rate of 1 unit of time per unit of time. So the combination of those then tells us the whole search process for the buyers. They're taking as given what this distribution F is that they're facing, but they get to optimize on their choice of R and S. For the choice of R, that's pretty easy as long as the surplus is better than you're getting some positive amount inside of that integral, so your X minus P surplus is greater than the value of continued search, then you accept it. And so, of course, that RZ will change because the value of search will change over time.
And then there's discounting going on as well?
Yeah, the discounting is coming from the row over on the other side. So you're saying those future opportunities, for instance, if I'm getting a positive flow of utility during the grace period, this might be like I have a house right now and I don't want to get the new house earlier than I have to, then that row is going to take into account the fact that I don't want to give up the future flow of B before I have to.
So there could even be a scenario where you're gaining something, but the discounting is still disciplining the problem. Okay.
That's right.
I was just trying to figure out, because you could almost do it without a discount, I think, here, if the costs were high and you picked your parameters right. Am I?
Almost, yeah. It's very, so it would change which equilibrium we can get out as we get to that, the solution here. All right. Okay, seller side is a little simpler, in fact, because they're not going to have so much of a dynamic problem. They're showing up at each instant that someone appears to them, and they say, okay, well, I can produce this thing at cost C, and we're going to assume that C is strictly less than X, so that there's always beneficial trade possible anyway. They're going to make a quote, and then they have to decide, well, what price do I offer? I can choose anything that I want, but in making a choice, then I'm going to be limiting which people in the market are willing to accept that. So our expected profits are going to be the R minus C is telling you the producer surplus, really, right? The how much profit they make if the transaction happens. But then GZ is going to say what measure of buyers actually will accept that offer. And we have to be a little careful here on this GZ. Because different consumers are potentially searching different amounts, their intensity differs, you're going to get more quotes from people who are closer to their deadline. And so GZ takes that into account. It says, what's the probability, given that I got a request, that this person has Z or less time remaining in the market? And so if I'm really close to if I'm choosing a price that's close to Z equals 0, I'm saying, the term I'm going to use here is targeting. I'm saying I'm thinking about trying to get people who are at least with Z time remaining. I want to make sure that they're willing to accept this. And so anyone who has Z or less time, they're going to be the ones who are my potential customers. So by raising the Z, I'm giving more time, which means I'm lowering the R, but I'm increasing the G. Therefore, those could balance out. If there are multiple prices that have the same maximum pi Z, then we can have a non-degenerate distribution that spreads across those for our equilibrium F.
And the only place we have a mass of consumers is at Z equals 0, right?
That's correct. That's correct. Because they've flown in at the beginning in this kind of steady trickle, they continue to trickle their way down through until we get to 0. But there they do accumulate, and we'll have this mass of consumers there at the expiration. In fact, next slide here. Because the firms need to think about how frequently am I going to get these quotes, they need to know the distribution of the buyers as well as their effort that they put into search. So HZ is going to be the kind of similar idea to GZ, but saying, let's just ask how many people are there with Z or less time remaining. And then if you take the derivative, that's going to tell you the relative density of each of them. So we're going to model this in steady state, which requires that inflows at any state have to equal the outflows from that state. So for instance, at time cap T, the inflows are that steady trickle of delta, more customers that come in starting to look for the product. That's also the outflow of H prime, though, because those people immediately start having their clocks tick down. So they need to be replaced completely every instant as the ones who come in immediately start going down the chain. From there, the inflows to the next state, Z, is H double prime Z. It's like how much did it change between those two periods? And that's got to be equal to the number of people who accepted an offer during that time period. So there at time Z, there were H prime people, or relative density of H prime. Of those, mu plus lambda S of them, that was the rate at which they bumped into some seller. And then of those, the acceptable prices came with probability FRZ. That is, F is the cumulative distribution of prices that were at or below RZ. So in total, we say on the right-hand side is saying, here are people who got an offer and we're accepting the one that they received, that's how many people are going to be leaving the market between this time z and the next instant z minus epsilon. Same sort of reasoning is used for that mass of people who are going to be at state 0, but instead of using, because there's a mass of them there, we say, how big is that mass, H0? And all of the prices they get quoted in equilibrium will be acceptable. So that's why F has disappeared here. It's just a 1. Of course, the rate at which they bump into someone, that's till it takes time to find someone, even though all of the prices are acceptable. That will tell you how many people left the market. And then H prime 0 is telling you how many people came into the market from having just expired. So they came from H epsilon, Z equals to epsilon down to 0 in that instant. And then finally, this is just the conversion for the firms of saying, to calculate that GZ from the previous slide. They want to know not only how many people there are, but how many quotes do each of them produce. So this is the summing up of those for all of the people of type Z or lower. Here's how many quotes they request in a given instant of time. Okay, steady state distribution. So equilibrium definition here is, I think, what you would anticipate. It's, for one, the Bellman equation is going to tell you how do the individuals maximize their utility, what's the strategy that they should be employing. The steady state conditions ensure that it's balanced over time. And then the profit maximizing means that they only offer prices that are going to maximize the profit. Anything else that they don't offer needs to be weakly less. All right, so the most of the remainder of this, I want to take you through the pricing outcomes here. And we're going to start by looking at this in the case in which search effort really doesn't do anything for you. So this is, you can think about this as exogenous search intensity, because what's going to happen is if lambda is 0, there's no reason to put any search effort in. You're just going to accept mu as the rate at which offers come, but it'll be the same mu throughout your whole search. The reason we look there is that we can do full analytic solution on this. And it also informs us as we move to the endogenous case where search is effective, the search effort matters. So let me talk you through this fast. So first, the solution process here. The trick in terms of being able to get the analytic solution is that this continuous Bellman equation that we set up can be translated into a second order differential equation, all in terms of the reservation price. That differential equation has the solution that you see there. Basically, we solve this out, and it breaks up into 2 phases. There's this critical time y star, which says from this time on, there's going to be a dispersed price. That is, the firms are going to be willing to target people within that. And in that range, it has one form. And then there's this above y star, that is for the people who are fairly early in their search. Firms mostly ignore them. And I say mostly because there's also a possibility that they could be targeting new entrants, even though they're not going to target the people between y star and cap t. They say, the people who just enter, we might want to target. That's the atom A star. That's a mass of firms offering exactly RT to say, I'll catch some of the people who just got into the market. But then I'm going to ignore the people in between. Yes, if I'm offering RT, I'll be selling to some of those people, but I'm not going to be targeting them. Couple observations. So this is, I'll tell you, this is the solution, but I'll show you some pictures here in just a second. But a few things that we can see from just the solution. Number one, you're going to have that in equilibrium, the reservation price is always increasing as you get closer and closer to your deadline. And in fact, it's kind of accelerating as it gets closer. So as you get close to the deadline, it matters even more. You can also see from the first line on the solution, you're always covering at least that cost C. Of course, the firms wouldn't sell it to you if you weren't covering that. But the second term tells you how much markup the firm is getting from you, which depends on first the size of that gap of utility, B minus D, that tells you how big the penalty is basically for crossing your deadline. If that's bigger, they're going to get more markup out of you. That's pretty intuitive. If you're also a higher row that appears in the exponential terms there, that's also going to make it so more impatient, therefore a higher markup that the firms can charge you. And then mu, on the other hand, is telling you that the closer that, so the more frequently you're getting offers, then the less desperate you'll be. And so your willingness to pay is lower.
What do we get when B equals D? So if there was no deadline, does this
No
just kind of get
deadline.
you a continuous diamond paradox under the kind of?
Yeah, so at that point, the question at that point is this wouldn't be the appropriate solution for it, because at that point they just all charge the same price, right? And if they've got the monopoly power, then it'd be the diamond paradox of just charge X. Yeah. The price distribution looks like this, and as I mentioned before, there's kind of these two phases. You can see in the first line there, that's that atom that occurs at RT, and from that point all the way to RY, they don't offer any additional prices in between that range, and so it stays constant for this cumulative distribution. And then for this next phase from Y to 0, they offer prices to target all of those people according to this this log function. And then if you run this all the way to R0, it turns out that there's a gap between the second line and the first line. There's going to be an atom there at R0 as well. So we could have up to 3 atoms in our solution, along with this continuous distribution between R0 and RY. So here's some examples. There's really 5 different ways that the equilibrium can turn out. Some of them are pretty intuitive. This is one of the intuitive ones. Suppose that the penalty is small, not 0, as Daniel was saying, but suppose it's just a really minor penalty. People are eventually going to want to buy this, and the market will discipline what the price is that they can charge. But the firms are going to say, there's no point in trying to target anybody except the expired ones, because the penalty is just so tiny. They're willing to wait this out. And you can see, I mean, the reservation price is increasing. For a lot of it, for reference here, the cost is 100. So a lot of this, they're not even willing to pay enough to cover marginal cost from when they entered. So obviously you're not going to be targeting them. But even in the close to the end, you say, well, there's not enough of them. And there are so many people who have accumulated past their deadline. Those are the ones that I'm going to strictly target. So our entire mass there is shown in the middle graph there with a mass at 1. More interesting is if you increase the penalty, that is D is lower here, the sellers are going to still ignore the earliest offers, but not all of them. So you can see again, the reservation price is still doing this steady climb, but the firms look at this low price that they're willing to pay early on and say, well, even though technically I could make a markup on that, the number of people that are there doesn't justify it. It's not worth, I don't get so many more customers that it's worth it. And so they skip all the way in this picture up until they've got about 9 periods remaining. And then there's a jump. One of our atoms occurs there. In fact, a large jump of, like almost 75% are going to offer that first price that at R9. And then there's this continuous range in between, and then you see the second jump at R0. And then in the third panel there, I'm showing you that the profits are in fact constant through all of that range, making it possible to keep this as a mixed strategy. And they definitely don't want to offer anything higher than R9. Kind of the important thing to take away from this in terms of the way the solution goes is that the reason we need those atoms is kind of I guess I could say 2 things about it. First, in that continuous distribution portion from R0 to R9, what's happening there is that the changing distribution on the steady state as people are leaving the market is exactly being balanced by the changing increase in the reservation price. So the solution comes from making sure those 2 are going to work together to exactly cancel it out. And that's going to require us to have exactly the climb that we have there in that part of the distribution. A little bit less obvious is why you need atoms at the top and the bottom. But essentially, this is, it's a differential equation, so we're going to have boundary conditions. But those boundaries are balancing the profits to make sure that as we do start offering, if you're just barely easing into it, then it would actually make a extra profitable to be offering right there at R9. And so that there'd be more and more firms saying, no, let's target that instead. So in equilibrium, that balances out, that they say, okay, since there's a lot of people offering here, it reduces the number of people who will continue flowing on down into the remaining lower states there, getting close to their deadline.
Can I ask just a quick question on the very small dispersion one?
Sure.
Does the one where D and B are very close but not the same. So this one, yeah.
Yeah.
You're still getting so what's the price then that ends up being charged?
The price that gets charged is that top price on the RT graph of 102.
Okay.
Yeah.
So it's basically going to come out to be just as if they were equal in how you charge the tail.
Yep.
The only difference is that they weight. Does that then mean that it's actually worse if they're not equal for consumers?
Let's see. So if they were exactly equal, like taking this to the limit, it's going to get closer and closer to 100. But that's assuming that there's no market power for the firm. So that's why it's not going to the diamond paradox right away. Okay. So this is the late dispersed equilibrium then, and I think this is kind of the one that that Noriah and I think about the most. Of like, it seems a bit intuitive that firms are going to say, "Yeah, I'm not going to try to go after the pickiest customers. I'm willing to wait a bit until they get a little more desperate." However, if we can make them a little more desperate by changing the penalty, so here I've made it even bigger. And at that point, the interesting thing is that as you make it bigger, coming back to the late dispersed equilibrium here, they're going to go earlier and earlier. You're going to see that this atom at the lower price is going to get closer and closer to cap T. But eventually it hits cap T because the penalty is so large, and then it bounces back. But as it goes back, it leaves an atom at cap T. So here in this example, you see that at 12, there is this large atom. Again, like 70% of the offers are to people right as they enter. And those offers will be acceptable to people at any remaining point in their search. So essentially the firms are saying there are enough people that enter this market that it's worth targeting them, even though their price is fairly low. In this example, they're only willing to pay like $106, $107. But there's so many of them that it's worth it. But after that, they say, yeah, but then they start declining really fast because we're making lots of offers. So there's not a lot of them in the next period of time here. They haven't accumulated much. And that's why you see in the profit graph, it's falling there right after, going from 12 all the way down to about R9. They say there's fewer and fewer people because we're making so many offers of RT that it's draining the market. The thing that eventually makes it reverse is that people start getting desperate enough to raise their reservation price. And so eventually that reservation price climbs enough that it says, okay, now it's worth targeting those people again, even though there's not a lot of them. They pay a ton, so I'm willing to target them. And so you see there's that little jump at RY, and then the continuous distribution, and then again the jump at R0. And then again, if you continue lowering the penalty further, eventually this gets to the point that on this RY gets closer and closer to R0. It takes longer and longer for that ramp up in reservation price to counteract the decline in the number of people as they're getting drained off from RT offers. So eventually it just becomes you only offer RT or R0. The two endpoints are profitable, nothing in between. And then final step, you keep raising the penalty. Eventually it's going to be strictly profitable just to offer RT. You say, you know what, I could target all these other people, but there are the people who are entering are desperate enough that I can get enough money out of them And because we're all offering this price, there's not enough people in the remainder to make it worth targeting them. So those 5 equilibria are what can happen. In fact, it's the only things that can happen. And the second proposition we'll see in a moment says that there's no overlap between them. It's a unique equilibrium for each of those. If you're interested, the way that you pin down those, the critical time Y and the atom A, those are the two things that entered into our solution before, these two boundary conditions are what determine it. Essentially, the first one is ensuring that the buyers, as they're starting the market, we've got to make sure that the Bellman equation matches up with when they continue in the dispersed portion. So this is like matching up at RY to make sure that the two reservation prices are actually continuous there. And therefore that the Bellman equations are properly estimating from the beginning what my whole search experience will be like. The second one is basically doing the same thing for the sellers, except it's checking the willingness to deviate, of saying, am I willing to take a price that's just a little bit lower than RY? Because that's always where the deviation happens. That it ends up saying, well, maybe I should try to target a little bit earlier, but this ensures that it's not going to be profitable to do so. All right, so 5 minutes to get us to the endogenous portion.
You have more like 8 minutes because we started late.
Oh, great, fantastic. Well, I won't speak quite as fast then. As we move to the endogenous intensity, two things happen. First, of course, we're going to have to solve for SZ. And that's going to really mess up the process of doing the solution of the Bellman equation like we did in the exogenous case, because the SZ has extra terms running around. The good news is we can still do that translation. And especially the good benefit of using the quadratic search cost is that it makes it so that the optimal search intensity, SZ, is going to be chosen to be equal to the expected benefit of search. And so that allows us to at least rephrase SZ in terms of our reservation prices, RZ and RZ prime. And that keeps it that we can eventually get this all into a single Bellman equation. Still second order differential equation, although it's a lot messier. To give you an idea, that's what it looks like. So this SZ term, that's saying what your expected benefit of search is in terms of the reservation price. On the second line there, you'll notice that if I were to set lambda equal to 0, like we did in our kind of baseline case that we've gone through, that whole term on the right-hand side of the equality would just be 0. And then that gives us the differential equation that we solved for the baseline case. So that adding lambda in does make this thing quite a bit messier, but still doable. I guess if you're interested in the process here, there are some tricks that you have to pull in order to still calculate this, because even though we've got this differential equation that can be all in terms of R prime and R double prime, you can hand that to Mathematica and say, solve for this, but you need boundary conditions. And especially if you're doing it numerically, you have to know what those boundary conditions are exactly. So that's the other trick. When we give the paper circulating more, you can dig in on that if that's something that would be useful for you. Here's the solution that we get. And for convenience, I've plotted here, this is a late dispersed equilibrium. And I'm comparing in the dotted line. This was an exogenous example that we would have done from before, of saying, let's only target people. In this case, I've set up the parameters so that you only target people from like 10.5 on. But then under the same parameters, I now introduce a little bit of effectiveness. So I increase lambda from 0 to like 0.25 and say, let's see what you guys do now that you're given the option. Here's the interesting things. Number one, you can see that in the first panel, reservation price is still increasing. It's at every point in time, it's lower than it would have been. So that tells you that by being able to have this option to search harder, it's allowing you to be more picky about what you accept. You lower your reservation price and say, well, I'll just work harder if I don't find what I want. And in fact, you do see that you work harder. Initially, you don't work at all. Your S is equal to 0 all the way up until this time about 8. Then you start ramping it up, and that also increases, and it actually ramps up with a higher rate as it goes. One interesting result that we can prove generally, even it doesn't even need the quadratic form of the search cost, that is that you're never going to do any search before they're actually offering prices that are acceptable. So you notice that in the price distribution, nobody offers something below R8. And so there's no point in doing any search then. But it also means that you don't just jump up and start search effort at R8 either, because when you first start receiving offers, those offers are just barely making you indifferent. And so you say, oh, well, great, someone's offering R8 now, but if I accept it, I'm no better off than if I just keep searching. So there's no reason to like work extra hard to get more R8 offers out there, even though they're available now. So we always have this nice continuous ramping up of your search intensity. I've on the first panel, I've noted where the Y star is, the point at which firms start making offers that are acceptable to people, and you'll notice that that has moved later. That's a kind of interesting result. The firms say, well, now that you're going to be searching harder later on, then that's kind of shifted the distribution of what offers are going to be accepted. There's going to be more people making requests for quotes late in their search, and so they're kind of shifting the balance that way. And so I might as well target them. But also these people who are early on, they've also got a lower reservation price, so I'm just not interested in targeting them anyway. So both of those things are kind of shifting in the same direction of saying, well, let's hold off and target later. The last thing, looking over the price distribution, I think is kind of one of the more exciting parts of this, is thinking through, well, how does that affect the prices that are offered in equilibrium? And of course, you can see that there's this difference between like R10 and R8. That's showing you that some of the low prices that were there before have now gone away. They're not targeting those people. That's not great for the consumers. And then even once they have that initial jump, it's not jumping quite as high, and it's not climbing quite as fast during the continuous distribution of the price distribution. So we've kind of worsened the price distribution in two ways, and so there's a bigger block of offers at R0. So I guess the way to say this is that the firms are in fact changing their prices. Now remember, I'm quoting over here on that's Z, that's on the axis, not the price, right? And over here on RZ, you can see the prices have changed. So it's not necessarily the case that all of the prices are worse off, but who's getting targeted is certainly changing. And so you could ask, well, is it better or worse then? I mean, the RZ is lower, but the price distribution is targeting more people late in their search. How does this play out? And the net effect of it is that people are better off, even though the price distribution is targeting them worse. On net, it's the sellers are preying on more of the expired, but the expired are paying a lower price, so it's okay. So I've only plotted this for the late dispersed equilibrium, but the other 5 equilibria still exist here, and they can each be solved out with the search effort. And I've at least for all the parameter values I've played with, the way that this plays out is pretty much the same in terms of lowering the reservation price by having the option to search more. The one thing that can vary with parameter values is over on the distribution of prices. Depending on how effective search is, you can actually have it that the blue line is above the red dotted line. So you're actually getting a better distribution.
Just so you know, you have a little bit under a minute.
Okay, great. Well, that's great, because here's the conclusion slide. So I hope the things that we get from this is that we do get interesting distribution of prices here, not only with the continuous distribution from the continuous time model, which is kind of, I guess you might expect should be possible, but also with these atoms that occur as well. I think that's kind of an interesting strategy. Especially, I think that early equilibrium is kind of interesting, where you target people as they come in. You'll target them at the end, and you might do some targeting in the middle. But there's reasons to just ignore the people in between. That's, I think, an interesting, rich dynamic. And then also this idea from when we add in the search intensity, we see that there's this kind of strategic substitution between I can lower my reservation price because I can search harder. And the pricing of the sellers kind of moves the other direction, but it only partially offsets that. And going beyond this, we're kind of thinking through other places we could observe search intensity. Labor market, of course, comes to mind, and that's one that we are considering. But in terms of consumer search, we've also been thinking about the kind of visits to websites that can be tracked through cookies, or also these repeated auction attempts that we've explored before. That's it. Any questions?
Thank you so much for a great presentation. And yeah, ask questions as they come to you.
Yes, one thing I'm curious about. So one of your motivations was fatigue. And apart from this deadline, it doesn't seem like you have changing search costs over time. Like, assuming I keep my search intensity the same, the search costs are fairly constant. The experimental search literature that has looked at fatigue, Brownflin Schotter would be a good citation if you're not familiar with that. Basically finds that a good model for fatigue is search costs increasing over time. Obviously, it's a complex model, and so saying how would it change if you change this fundamental aspect is not easy, but I'm curious if you have any thoughts about search costs increasing over time.
Yeah, thanks, Ben. So yeah, this is a kind of a discrete jump in search costs, but we have thought about what would be the consequences of having a increasing search costs, but moving continuously over the whole time. And so, although the version we solved, it's an exogenous process, right? Like, I know when I first started that my search costs will go up in this steady deterministic way. And we're actually able to solve that out. As long as the functional form is fine, we can actually still get the closed form solution. But it's kind of limiting as to which functional forms you can use. More generally, we can still write down the differential equation, and we haven't tried out like how easy it is to solve out numerically. But from what we've learned doing the endogenous search effort, I think that we should be able to pull that off just fine now.
Okay, thanks.
I appreciate the reference there.
Well, as long as I'm handing out references, I didn't see Morgan and Manning in your reference list either.
Oh yeah. Definitely.
Any other questions? So I think one that's just kicking around that I'm having trouble tracking because there's so much going on in the model is just when consumers are going to be better off or worse off, right? Because if there was no pricing going on here, it's pretty easy to see, it's going to be worse when this happens, better if this happens. Is there anything kind of unexpected that happens due to the feedback loop of now firms picking prices? and being able to target different groups.
So one thing I didn't present because I was anticipating not having the time are the comparative statics, which is I think where we get the best feel for that. So in terms of keeping track of welfare, the best way to do that is look at RT, because that's going to be a proxy for what your expected value is as you enter the market. So as we went through those 5 equilibria, you could see that RT was going up, and so that in itself is telling you that the value of search is going down. So that's useful as kind of a shorthand for keeping track. In the comparative statics, we've looked at things that, and some of them are intuitive, like, bigger penalties are bad. The interesting one is changing the amount of time you have, the change in T. It's not always better for you to have more time. Because the downside, like in a late equilibrium, if you expand RT, then that means there's going to be this dead period where nobody's getting offers, and that still exists, but it means they accumulate more so that when they do come in, they hit with a vengeance. And so it shifts the price distribution, so it's worse for them. There's a few other comparative statics like that have some kind of surprises to them, but yeah, I think that's kind of one of the fun aspects of it. We haven't worked those out on the search effort version of this, and so that's the next step for us to see, at least in numerical examples, to see if that still holds out.
Brennan, could I just pick you up on the continuation of what you just said? I think you were then talking about what happens if big T gets larger. And I'm guessing you were talking about everybody's big T at once.
That's right.
And so I had this naive question. I agree with that, Dan, the model's a little busy. And actually, footnote, when you were talking about targeting consumers, I thought you were, for quite a while there, I thought, oh, you must be talking about price discrimination. You must be observing how long.
Oh, yeah.
Well,
yeah.
Sometimes it takes me a while to undo the, anyway, that's just a minor comment, right? When you say targeting,
thank you.
Now I've lost my thing. Yeah, so my simplistic way, I was wondering, on the one hand, do I want to start shopping for my wife's birthday present before everybody else is doing so, before they think? And that's actually leading maybe to something a little bit more interesting, which is sort of what are the externalities involved, maybe in terms of, which you probably can put together from what you just said. And if I go a bit earlier, I don't know, anyway, any further thoughts on what you were just talking about a little bit?
Yeah.
Does anyone else has something?
That is actually a very interesting question I hadn't thought about. For kind of, if you gave a consumer an option for unilateral deviation on when they start, would it help them? I think on any of these equilibria, the solution of going earlier is not going to help them, given that the price distribution is going to stay the same. They're only going to be more, have even lower reservation prices before that, right? And so they're not going to find anything that they're willing to buy. The more interesting one is going the other direction of saying, well, should I just stay out then and forego getting B, which might be positive, but maybe that's a good thing since I don't have to put in effort as well. I should actually calculate that out and check.
I like the idea of rationalizing procrastination. Brennan's model says, okay, it's fine.
That's fine. They're not even looking for me anyway.
Right, that big hole in the middle, unless I hit it on the initial buzz. Yeah.
That's right.
Yeah. Anyway.
Yeah, I also was thinking about what would happen if they could essentially just stay out for a little while and be passive. But related to that, so kind of, I'm always curious what you can do with a model and what you can't. And I think what I'm about to suggest is in the realm of can't, or maybe shouldn't. But what if like it's a deadline that's common knowledge and holds for a mass of consumers. So, I am not alone in forgetting Valentine's Day in a given year. And there may be other people who forget that same date or Christmas or the lead up. Are you able to get some sort of interesting dynamics in the lead up? Maybe in the case where you don't allow for search intensity to vary, but
I haven't done this with search intensity, but with the exogenous version, I've played with it some. If the deadline is common knowledge and everyone's the same, then you're going to end up just getting price discrimination at every point along the way. Like, surprise, all the prices are higher. we know we know that you've been procrastinating, and here you come. Now, the interesting one is if you do something that's more like a stall model where there's some shoppers and some procrastinators, right? So then you've got there's like they're passing each other over time. The procrastinators are slowly coming into the market while the early shoppers are slowly exiting the market. And that's one that I've got a toy version of the model working on, but I want to continue fleshing out so that it's a little more general.
yeah, I was thinking of like half of them have one deadline and the rest are just normal, right?
Yeah.
This is really an interesting model, but I don't tend to think about continuous time search. So it's new territory.
Yeah, I mean, it's the value in this is just that it's able to smooth things out for the solution. But it does take a little getting used to. Like, I don't know, it feels like putting your shoes on with the wrong foot or something.
Well, and remembering some math that
Right.
admittedly may have faded over the years. So I just wanted to, I'm going to end the recording here. Thank you so much for a great presentation. We'll keep the room open, but I just want to end it here.